Let's do another example of graphing a system of inequalities by hand. And another thing to mention is your graphing calculator can graph these. It takes a little bit of maneuvering, and you could use other computer programs to graph these. But what I'm trying to emphasize is why these make sense and how we can kind of interpret the meaning of these graphs. Basically, it's giving us regions of acceptable outcomes. And in the next section, we're going to call them feasible regions. And what we're trying to figure out is what are valid options when we're, say, for example, we're trying to manufacture. We want to know what things are allowed and what things aren't allowed. And the inequality represents what is an allowable constraint. But anyways, let's continue with the algebra. So in this case, again, if we're following the step-by-step thing, step one is to graph the boundary lines. And remember, boundary line just means change it to an equals sign and graph. So like in each of these, we could imagine our first equation as y 2x plus y is equal to minus 2, and negative 5x plus 3y is equal to 27. And I want to graph those lines individually. And then after I graph the boundary lines, I figure out where to shade. And what I could do is I could solve these for y so that I would put it into slope-intercept form. That way I can graph it a little bit easier. So the first equation is going to have a slope of negative 2 and an intercept of negative 2. The second equation, I would want to add 5x to both sides and divide by 3, which would give me 5/3 x plus 7. So the second equation is going to have a slope of positive 5/3 and an intercept of positive 7. And so I want to graph each of those lines. But there's an important note here is that it says if the inequality is greater than or less than without equality sign, we want to use a dotted line to graph. Whereas if it's greater than or equal to, we're going to use a solid line. Like I did up here, I use solid lines, but basically here we want to use dotted lines to graph it instead. And after I do it, I'll explain why this, what does this mean? So the first equation has an intercept of minus 2 and a slope of minus 2. So rise negative 2, run 1. So that should look something like this. And I'm going to use a dotted line through these points instead of a solid line. Go ahead and finish this out, something like that. Cool. And the second line is the line 5/3 x plus 7. So that would have an intercept up at 7, 3, 4, 5, 6, 7, and have a slope of 5/3. So rise 5, run 3. 1, 2, 3, 4, 5, 1, 2, 3. So right there. 1, 2, 3, 4, 5, 1, 2, 3. 1, 2, 3, 4, 5, 1, 2, 3. Something like this for its slope. And its positive slope, so it should be going up to the right instead of down to the right. And there we go. So this is a little bit awkward looking with my arrows. But anyways, so why do we use a dotted line is the next point I wanted to bring up when we have greater than without equality. But the reason is because if I'm looking at the equation y equals negative 2x minus 2, that is going to be represented by the line itself. But if I'm looking at the inequality, notice that it doesn't actually include the option of equality, right? 2x plus y must be greater than minus 2, not equal. So what it's implying is that it is not equal, meaning the dotted line means it's not part of it. And it's very similar to when we graph simple inequalities, as we did before. And it's kind of like the difference between an open circle and a closed circle. Like I said earlier, right? If I have x is greater than or equal to 2, we represent that using a closed circle and a bracket when using interval notation. But if we change this to x is equal to 2, or sorry, x is just greater than 2, right? What we're taught to do is we're taught to use an open circle or a parenthesis when using interval notation instead. What the heck did I just do on my tablet? So I'm trying to write on my tablet and it is going bonkers. There we go. But basically the difference in the notation is instead of x being greater than or equal to, x is just greater than 2, meaning that it's all the values bigger than 2, but it's not including 2. And that's just what open dots mean in a mathematical graph instead of closed dots, or parentheses interval notation as opposed to the brackets. But when we're talking about 2D graphs, that's what dotted lines typically mean. They represent boundary lines or sometimes other things like asymptotes, but they don't include this as part of the answer. So really the only difference is these lines are not part of our answer, whereas up here, technically these endpoints on these lines are part of the answer. And again, there is no such thing as interval notation in these. It's kind of too complicated to write like using a mathematical sentence. That's why we have to use graphs for these regions, because it's kind of hard to understand what the heck's going on without having a two-dimensional graph. But anyways, last but not least, we need to figure out the shaded area, which can be done in exactly the same way as before. So you could use test points, which is totally fine to figure out which region works. But let's do it using my first method, which was to use the inequality direction to do it as well, because that's always faster. And you don't really have to do any math. But what I wanted to mention is you got to be careful about the direction of the inequality. What I recommend is while you're solving it for y, make sure that you're also dealing with the inequality at the same time. Because if I was to, write this one using its inequality instead, that would have been y 2x plus y is greater than that. And when solving for y, it would leave me with y is greater than negative 2x minus 2. So that would have given me all the values that are above negative 2x minus 2. And so that one would be that should be my shaded region for inequality number 1. And for inequality number 2, it was less than originally. So if I was solving it like this, I would have had a less than here, and a less than here. But remember, the direction of your inequality could change if you divide or multiply by a negative or whatever. All standard rules for inequalities apply to these as well, and any inequality in general. So this one is y is less than 5x minus 3, which would be that region. And summarizing, it would be below this line and above this line. So ultimately, it's going to be the shaded region to the right of them all. This is the region that should work. And I could confirm with a test point, say for example, using the origin again, if I plug in 0, 0 into these, I would get 0 plus 0 is greater than minus 2. That's not right. So I goof something up. Oh no, that is right. Sorry, I confused myself, right? 0 is greater than negative 2 because 0 is greater than any negative. And if I plug in 0, 0 here, 0, 0 less than 27, yes. So I confused myself, but my point stood that any test point in that region should work. And once I find one working test point, I will shade the rest of the region. Anyways, that wraps up how we graph systems of inequalities. And in the next section, we're going to do very, very different things, but ultimately we're going to come back to this exact math, and we'll see how this is useful in a few of the examples.